So far in this course, we have introduced the basic life cycle of a clinical research study. We start with an idea, which leads to a research question and a research hypothesis. We then determine the primary outcome of the study. In this video, we will discuss the next phase of the life cycle, designing a study and collecting data. We will discuss the two main types of research studies, how many individuals are needed for a research study, collecting raw data, and producing analysis datasets. When clinical researchers are trying to answer a research question, they need to select the type of study design they will use. The study design describes the strategy for collecting data and drawing conclusions from those data. There are two main types of designs that clinical researchers might use: observational or experimental. There are many types of observational and experimental designs, but for now, let's try to understand the basic differences between these two types of designs. Our goal is to give a general overview and encourage you to meet with a quantitative scientist, such as a biostatistician, to help you design a study and collect data in a way to ensure that your research question can be properly answered. Experimental studies. One of the most common experimental study designs is when the researcher randomly assigns study participants to specific treatments or interventions. The interventions may involve medical drugs or devices, medical procedures, or behavioral strategies designed to change a participant's health behaviors. After assigning participants to experimental groups, the researcher then takes measurements on the participants to see whether the people who receive one intervention do better or worse than people who receive the other intervention. Such experimental research designs may be used to compare a new treatment approach to an existing standard of care, or they may compare existing interventions to determine which is optimal. Let's consider an example of a study that examined ways to help college students with depression. One of the challenges for students with depression is remembering to take their antidepressant medication. Tracy Hammonds and her colleagues conducted an experiment in which they examined whether a smartphone app that sent reminders would lead to better medication adherence among college students with a current prescription of antidepressants. Students who agreed to participate in the study were randomly assigned to either a group that received reminders via a smartphone app or a control group that did not receive reminders. Participants in both groups allowed a research assistant to count how many antidepressant pills were in the bottle at the beginning of the study and 30 days after the study began. If a student was adherent, then there should have been about 30 fewer pills left in the bottle at the end of the study. If fewer than 30 pills were gone, it meant that the student did not take all of the pills they should have. The primary outcome of the study was the difference in pill count after 30 days, and the primary exposure was study group, receiving the reminders or not. The research hypothesis was that those who received the reminders would have a larger difference in pill count and thus be more adherent than those who did not receive the reminders. At the end of the study, the researchers found that students randomized to receive the reminders were slightly more adherent than students in the control group who did not receive the reminders. The benefit of randomization is that it produces comparable study groups that are similar in all aspects and characteristics except for the treatment intervention. Observational studies. In contrast to an experimental study, an observational study design is one in which the researcher just observes what's happening without intervening or trying to change anything. This design is useful for answering questions about how things are, like what happens over time to people who have some disease, or we might predict what patients are more likely to develop more severe problems. Observational studies are also useful for exploring the reasons why certain patients might do better than others. Neither the individuals under study nor study variables of interest are manipulated in any way. They are observed and measured as is. Let's consider a recent example of an interesting study that uses an observational design, published by Johnson and colleagues in 2018. These researchers were interested in understanding more about patients with cancer and the types of treatments they choose. Conventional treatments for cancer include surgery, radiation, chemotherapy, or hormone therapy. However, many people choose to supplement their conventional treatments with complementary medicine treatments administered by non-medical personnel, which could include herbal remedies, acupuncture, massage, or special diets. Dr. Johnson and colleagues wanted to know whether patients who supplement their conventional treatment with complementary medicine treatments had different overall survival than patients who use conventional treatments alone. To answer this question, the researcher used an observational study design in which they obtained retrospective data from the National Cancer Database on patients from 1,500 cancer centers from around the United States. This database contains information on patients' types and severity of cancer, treatments they received, other health conditions, and demographic characteristics such as age and race and ethnicity. The researchers used this database to identify patients who use conventional treatments and those who use conventional plus complementary medicine treatments, and if the patient died, they ascertained the time and cause of death. The primary outcome was time to death, and the primary exposure was treatment type. The researchers found that fewer patients who used complementary medicine treatments as a supplement were still alive after 5 years, compared to patients who did not supplement their conventional treatments with complementary medicine. Experimental or observational study. Both study designs come in many different forms, and it can be difficult to determine which approach addresses the research question of interest. A person with expertise in study design should be consulted to help decide what type of experimental or observational study should be conducted. Both designs have benefits and drawbacks that must be considered. Experimental designs are much better for deciding whether an intervention of interest caused improvements in health. However, experimental studies tend to be expensive compared to observational studies. In some cases, it is impractical or even impossible to use an experimental design to test the effects of an intervention. In such cases, researchers might use an observational design to try and strengthen their conclusions by using special statistical analyses to help eliminate alternative explanations for why people receiving different interventions have different health outcomes. Data collection. The design of the study must also consider what measurements and variables are needed and how the measurements will be collected. For example, a study can be designed to measure individuals once at a single point in time or to collect repeated measurements on individuals over a length of time. Single versus repeated measurements will have a huge impact on the methods used to analyze data and what types of conclusions can be drawn from the results of the analysis. It's also extremely important that the researcher is collecting the right measurements for the research question. Of course, the researcher needs the measurements of any primary exposures and outcomes, but may also need to collect data on other factors that could influence the primary measures, and this is especially true for observational studies. Basic demographics are standard: age, sex, race and ethnicity, SES measures, etc. But other characteristics could be important to have. The researcher and biostatistician can work together to make sure all necessary variables are discussed during the design of the study. Sample size and power. Lastly, in designing a research study, a common question is, how many individuals do I need? This number, or sample size, depends on several factors. 1. Minimal clinically important difference. 2. Variability of the primary outcome in the population. 3. Type 1 error rate and desired statistical power. 4. Statistical tests to be used in the primary analysis. The researcher, together with the biostatistician, determine values of these factors, with each providing critical information. The researcher has expertise in determining the first two values, and the biostatistician has expertise in the latter two values. Using these values, the biostatistician can determine the required sample size to achieve the study goals. Minimal clinically important difference. Recall the null and alternative hypotheses from the previous video. The researcher must decide how far away from the null the alternative must be in order to conclude that the alternative is true. That is, the researcher must determine how big a change is required in the primary outcome of the study for the results to have a meaningful clinical impact. For example, in a study investigating medication intended to lower blood pressure, the null hypothesis might be that the medication does not change BP. That is, the average change in BP after taking the medication is 0. The alternative hypothesis would be that it does change BP, and the minimal clinically important difference is the amount determined by the researcher that BP must be lowered by the medication for it to have a meaningful effect. A mean change or decrease of 1 millimeter of mercury might likely not be enough to say that the medication has a meaningful effect, but a mean change of 5 millimeters of mercury might be clinically meaningful. Variability in the primary outcome in the population. Some knowledge of how much the primary outcome can vary within the population under study is needed to determine sample size. Estimates of the variability can come from previous literature of similar studies conducted in a similar population. Rough estimates can also come from pilot data, where the researcher enrolls a small preliminary sample of the population and obtains estimates of variabilities of the primary outcome measure. Type 1 error rate and desired power. Recall from the last video, the null and alternative hypotheses are mutually exclusive and exhaustive, meaning one and only one is true. In practice, we do not know which one is true, but the results of the statistical analyses will favor one over the other. If the results favor the alternative hypothesis when the null hypothesis is true, this is called a type 1 error. We generally want the chance of this type of error to be very low. Claiming that an intervention is effective when it actually is not is something to be avoided. The researcher works with the biostatistician to decide the type 1 error rate to be used for the study. The typical error rate used for most studies is 5%. When the results favor the alternative hypothesis when the alternative hypothesis is true, this is called statistical power. Power should be high to ensure that the study is successful and is commonly set at 80% or above. Statistical tests to be used. Finally, the sample size needed for a study depends on what statistical tests will be used for the final analysis of the primary outcome measure. The primary statistical method is determined by the biostatistician based on the research question, the study design, and the primary outcome. In addition to the factors above, other logistical considerations must be taken into account, including availability of budget, ability to recruit from a large population, accrual period for the study, anticipated refusal rates, and dropout rates for the longitudinal studies. The biostatistician can then utilize all of this information to estimate the required sample size for the study to have adequate statistical power to reject the null hypothesis for the primary study outcome. Raw data and analysis datasets. Once the study has been designed and proper infrastructure for successful management of the study have been put in place, the research team can start the study and begin data collection. It is important to collect, manage, and store research data using systems that follow appropriate data provenance principles. The term data provenance refers to the process of documenting each step of the data processing so that origin and transformation of any data collected from a study can be verified, thereby ensuring that the conclusions reached by the study are accurately based on the data that were collected. For experimental or prospective studies, primary data or real-time data collection is conducted. This may involve taking measurements on individuals and recording the values in a way that is secure, reproducible, and not prone to error. For retrospective studies, secondary data collection is conducted, meaning data collected by someone else for some other purpose is used. This typically involves extracting data from electronic health records, performing chart reviews, or using existing databases or national surveys. Regardless of whether primary or secondary data collection is used, the data should be collected using well-established data collection systems that incorporate data checks and version control, such as REDCap, a secure web application for building and managing online surveys and databases. Systems like REDCap can prevent data entry errors, invalid values, and unauthorized changes to the data. Spreadsheet programs like Microsoft Excel, which are widely available and easy to use, are often used for data collection but lack many of the key tools necessary to ensure that the data are reproducible. Once data collection is complete, the raw data and all changes made to the raw data in preparation for statistical analyses should be documented and securely stored. The analyst will perform data cleaning and data checks. Derived variables will be created as needed, for example, computing BMI from height and weight measurements, and analytic data sets will be created for use in statistical analyses. These are cleaned up versions of the raw data that are ready for statistical analyses. The process of converting raw data to analytic data sets should be done programmatically with well-documented code so that an independent analyst can take a copy of the raw data set, run the code as is, and reproduce the exact same analysis data sets. Prior to performing the primary statistical analyses for the study, these analytic data sets should be locked to ensure that no additional changes are made to the data after final statistical analyses have been initiated. Thus, with the help of a biostatistician, an appropriate study can be designed, including the type of study, number of individuals, and variables to be measured and collected. Data should be collected in a reproducible and error-free way using robust data collection systems. The analyst can create clean data sets that are ready for statistical analyses. In future weeks, we will turn our attention to the process of analyzing the data and drawing conclusions from the research study.